Hello, my name is Miguel Ángel Muñoz and I'm going to present my work, Data-Driven Strategies for Trading Renewable Energy Production, a joint work with Juan Miguel Morales and Salvador Pineda. We are all from the Oasis Research Group at the University of Malaga in South Spain. The objective of my work is to develop a mathematical optimization approach in order to improve renewable energy forecasting and trading. And we pursue a model that is able to leverage contextual information. Also, a model that is simple but effective and computationally efficient. We consider a situation in which an stochastic energy producer, like a wind power plant, it's aiming to sell its energy at day D. In order to do that, the producer entered an offer in the day ahead market the day before. Then the next day, the realization of the energy production becomes true. There is some penalties associated with the difference between the actual energy production and the day ahead offer, the offer that the producer entered in the market. And the producer has zero marginal energy cost and therefore usually enters an offer equal to zero. So in this context, we want to determine the best possible offer that the producer can do, taking into account the imbalance penalties and the structure of the market. This scenario can be modeled through the classical newsvendor problem, which is a very well-known single period stochastic optimization problem that has into consideration, or the objective of this problem is to minimize the cost of imbalances. On the left, underlined in orange, we have the underproduction cost. With E, we denote the random variable of the energy production of the producer, of the stochastic producer, and ED denotes the offer, the variable that determines the offer of the energy producer. We have C minus and C plus that are, as we mentioned, the penalties of underproduction or overproduction. And we impose some capacity constraints. The energy offer cannot be greater than the capacity of the producer. And this problem is well known to have an analytical solution, which is the cumulative distribution of this quotient. But in order to compute this solution, we need the true distribution of the random variable of the energy production. However, in practice, we usually only have available the empirical distribution. And this yields to poor solution, and because it does not leverage contextual information that we may have available, like forecast of neighboring power plants or categorical features like the day of the week, and so on and so forth. In order to leverage this contextual information or side information, we consider this linear decision rule proposed in the seminal paper by Van and Rudin, the Big Data Newsvendor, and which proposed to replace the variable of the optimal offer E sub D, super D, by a linear product, a summaton linear product of the contextual information X and some additional auxiliary variables Q that we introduce. If we replace this linear decision rule in the sample average approximation method, which is classically very well known and is the summation of the empirical across the empirical distribution, we yield this model, which also minimize the cost of imbalances through the training set T, imposing again that this decision rule that represent our decision, our energy offer is limited by the capacity of the energy producer. One of the advantages of this model is that can be easily reformulated into a inexpensive linear program. Also note that if we make the penalties equal to 1 for all time periods, we are instead minimizing the median of the energy uncertain variable. So we can use this model, with this simple and efficient model, to compute both a forecast and a trading offer, considering different penalties. In order to measure the performance of this model, we use the classical mean absolute error and root mean square error to assess the forecasting quality, and we use the objective function and the objective of the program to as the average opportunity loss to measure the cost reduction of the value improvement. We denote AOL. In our case study, then, what we have available is a set of historical data, the energy production of past periods, the opportunity penalties, the C, and some additional features that can be forecasts or categorical variables for some previous periods that are available at the time of making the decision. We also have some features corresponding to the AD that we want to determine the offer of the producer. We developed this computation in a rolling window setup, so we are moving through several days and the training set is updating accordingly. We use data of the Denmark bidding zone DK1. We've retrieved the prices from the TCO, EnergyNet, from the Danish TSO, and we retrieve the rest of the data, the forecast and contextual information from the Transparency and SOE Transparency platform. We use several years from 2015 to 2019. And again, the objective is to improve the TK1 onshore wind power forecast in order to deliver an improved forecast and an improved offer to enter in the market. In order to do that, we have assembled this setup. We built 4 models that are fit with the past energy forecasts and the historical energy production, and also some categorical information. Through this model, we produce an improved forecast based on the mean absolute error, and we enter this improved forecast in an additional model M5 to achieve an improved offer. Note that by improving the mean absolute error, we are also in some way pursuing the objective of improving the offer, the economic loss. So we have arranged these different models using different contextual information, like forecasts of neighboring countries, solar energy production, generation forecast, and total load, and we use some categorical information. Through this setup and these models, we achieve an 88.55% improvement in forecast and a plus 2% of average opportunity loss improvement. And we finish this presentation with some remark. We have developed a computationally inexpensive in-situ train model that is able to leverage contextual information and is tested on realistic case study. And we have improved the energy forecast and trading of our previous data. This is all. Thank you for your attention. And if you want to know more about this model, you can check our published paper, Feature-Driven Improvement of Renewable Energy Forecasting and Trading, that you can access through this QR code. Thank you.